I would like to thank the organizers for giving me this opportunity to present my work. So I'll be talking about the random connection model. Before I go into the connectivity problem, I would also describe some other related results before getting into connectivity. So the random connection model has been there for a while now. So it's a random graph, so I would have to specify what the vertex set of the graph is. And one can have a fixed number of nodes, but it's kind of easier to have to put a Poisson number of nodes, and then the results that you obtain for the Poisson can be what is called as depoissonized in order to obtain results for a fixed number of nodes. So the vertex set would be a Poisson point process of intensities, given intensity lambda in RD, the Euclidean metric, and for any subset. So what a Poisson point process means that if you take any subset of RD, the number of points would be Poisson distribution with mean lambda times the volume of A. And for two disjoint sets, I think again it's missing, the A and B are disjoint, then the number of points in A and B are independent. So now once we fix the vertex set, we need to specify how we draw edges between points in my graph. So given the Poisson point process, what you do is you're given a connection function G which maps from RD to the interval 0, 1. So we say that given any 2 points x and y in P lambda with probability independent of everything else, you draw an edge with probability given by G of x minus y. Right. So often our function G would be radially symmetric and it would just depend upon the distance between x and y, and so often we will just abuse notation and write G of the distance between x and y, right? Okay, so those are the, except in the end when we have a certain inhomogeneous random graph, there it would matter, it would be G of x comma y kind of thing, okay? So then it would be clear that things are inhomogeneous. Okay, so this graph has appeared in many applications in physics, in epidemiology, in telecommunication, wireless networks, and in biology. Okay, so this model was introduced in 1991 in a paper by Matthew Penrose, which extends. So there are some related models which have been studied quite extensively in the recent past. So one is a random geometric graph, or in 2 dimension, it's also called the Gilbert's disk model. Where this function G is very simple. So you take any 2 points, you draw balls of radius r around each of the point, and if these balls overlap, then you draw an edge, right? And this is a kind of a glimpse of what happens in wireless networks. You draw an edge if the following happens. Each node transmits with a certain power p, and so if xi transmits with power p, the amount of power that is received at a node xj is some fraction of that. So this L is the path loss function. It's typically like the reciprocal of some power of the distance, and so on. And then you have these independent random variables which are called the fading variables. And so this is the power of the signal received at xj from when the transmission happens at xi. And this is the noise, and this is the power received at j from all other nodes apart from I, right? So this is the signal, this is the interference. There is an interference cancellation parameter, and there is a noise, and so you draw an edge if this ratio is larger than t. So you can see that here there is a strong dependence between the existence of nodes. Now already in the random connection model, there is a dependence which is introduced because of the spatial proximity. So if A and B have an edge and A and C have an edge, it's very likely that B and C would have an edge, right? So there is some dependence, unlike the Erdos-Renyi graph. There's another very interesting model that was introduced because this random connection model typically does not display heavy tail distribution. The degree distribution is not heavy tailed, and so to fix that, it kind of makes sense to consider a model where at every vertex you have some weights, right? And the probability that any two a vertex at x and y are connected, okay, so this should be this W0 and Wx perhaps, okay. So the connection function would be something given like this. So you can think of these vertices as are not being homogeneous, but they are having different weights. Like you have a large city or a website which attracts a large number of connections and so on. So you have this inhomogeneity which is not quite coming from the underlying distribution of the points, but from the weights that are attached to it. Okay. Pardon? Which one? No, in this case, that's a typo here. So you think of this as the origin and this as x. So this is the connection between the node at the origin and x. Or you would want to write as g of x comma y, right? Yeah. So conditional on these weights, that would be the probability that x and y would be connected, okay? And these weights have a heavy tail distribution. There's also this random connection model with preferential attachment that was introduced and studied in Jacob and Mortars in 2015, where you add points sequentially and the connections would be formed based upon the proximity and also the existing degree distribution of the existing nodes. So we will consider the random connection model that was described earlier, the random geometry graph, and this inhomogeneous random connection model in this talk. Okay, so the most of the focus has been on this kind of phase transition, which is in the percolation or the thermodynamic regime, where what happens is that when you change the parameters a little bit, there is an abrupt change in the structure of the graph. So this is the kind of transition that has been studied mostly. And what happens is that the transition that is of interest is what happens to the size of the largest component, right? So if you think of the random geometry graph, you have a radius r and you keep increasing it. At some point, what happens is that you have a giant component. In an infinite system, this would translate to an infinite connected component, and one can show that there would be an unique infinite component. Whereas in a finite system, what will happen is that below the threshold, you will have components which are logarithmic in size, and then when you just go a little bit above, you will end up with, when you increase your intensity of your underlying Poisson process a little bit, you will have component which would cover a non-trivial fraction of the nodes, right? So this is the kind of phase transition that has been studied. Very quickly, some words about what happens there. So we can always, because I have my underlying Poisson point process is a Poisson point process, one can put a point at the origin. That would be like a typical point, and everything around it would still look Poisson. Let capital C be the component that contains this origin. We would say theta lambda is the percolation probability. That is the probability that this component is infinite, right? So the random connection model is said to percolate if theta lambda is positive. With positive probability, there is an infinite, the origin is part of an infinite component. Standard techniques would tell you that if theta lambda is positive, there would be with probability 1 an infinite component. One can adapt the Burton-Keene kind of argument to show that this infinite component will be actually unique. Okay. So we can, because this theta lambda is a monotonic function, we can define this critical intensity lambda c, which is the smallest lambda for which theta lambda is positive, right? And we will say that a non-trivial phase transition occurs if this lambda c is strictly positive and finite. Okay. So now if you look at this point at the origin, it's easy to, yeah. In the inhomogeneous model, I don't think it has been proved, but I would believe it would be unique. I mean, depends upon what kind of inhomogeneous model you look at. The one that with the weights, probably it should. I mean, this Burton-Keene argument is fairly robust. It is something to do with the geometry of RD and so on. So unless your space kind of grows very fast, you won't have enough space to accommodate more than one infinite component. So I would think that it would still be unique, but I haven't seen it written down anywhere. So the points that are connected to the origin forms by just a simple thinning argument would tell you that they form a Poisson process of intensity lambda times g. And so the expected degree of the origin would be this quantity here, right? So obviously there will be no non-trivial phase transition if this quantity is either 0 or infinite, right? And so in 1991, when this model was introduced, what Penrose showed was that indeed if G is integrable, then there exists a non-trivial phase transition in the random connection model. Now what happens in the inhomogeneous random connection model? So this is the model where the connection function, actually again I've just copied and pasted it from there. This should be g of x comma y, or you can think of, okay. So the probability of an edge, given the weights, probability of an edge between x and y should be this quantity divided by mod x minus y to the alpha. So it was proved, so in this paper here, that there is a non-trivial phase transition that occurs in one dimension if alpha beta has to be greater than 2 and alpha has to be between 1 and 2. And for d greater than or equal to 2, you need alpha greater than d and alpha beta greater than 2d. Okay. Then there is another very interesting question that one can ask here as to what happens to the percolation function theta lambda. Is the function theta lambda continuous? That is, what happens at criticality? That's a much harder question to answer, and that question, as far as I know, has probably not been answered for the random connection model. One can probably assume certain form for the connection function G and try to answer the question. But in this case, Deprez and Wuthrich showed that the percolation function is continuous for when parameters satisfy this condition. Yeah, so in this case you can prove, so in this case what happens, alpha greater than 2, you don't have a non-trivial phase transition. Okay?
Alpha equal to 0.5?
Where here?
In the
No.
equal to 1.
Alpha equal to 0.5, only if, so there is no non-trivial phase transition. Okay, it also depends on beta. Of course, alpha equals to 0.5, of course there will be no non-trivial phase transition. Right. So this result covers everything, all the thing. Whereas here, there is only a partial result. And as I said, this parameter regime is exactly the one Deprez, Rajat and Wuthrich have a paper preceding this one where they prove this result on a lattice. So this just extends it from the lattice to the continuum, okay? So this case is actually open. Of course, proving this is much, somewhat easier. I mean, this is a much harder question to answer. All right. So now we look at connectivity. So we want to look at the connectivity problem now. So in the percolation problem, what happens is that when you are above the critical parameter for the percolation, you have an infinite component, but then there would be a very large number of very small components. Those components are typically, the largest component would be logarithmic in size. And so now if you want the graph to be fully connected, it makes sense to slightly change the setting. And these are kind of equivalent. This is called as a dense network. So what we will do is we will put our point process, our vertices on the unit torus. This is just to avoid the edge effects. Otherwise, one will have to worry about what happens at the edges, right? Kind of computations become messy, but they can still be done. It's not hard. So you assume now that you have the vertex set is a homogeneous Poisson point process of intensity n on this unit torus, and my graph, okay, so this is for the random geometric graph. So if you recall what it was, your x and y have an edge if the distance is less than 2r, right? So the Campbell-Mackay formula tells us that the expected number of isolated nodes. So if I want the graph to be connected, the first step I would like to do is to find what regime where the graph would be connected, right? So in order to find that, the simplest thing to look for is isolated nodes, right? Because if there are isolated nodes, obviously the graph won't be connected. So I want to try to find a regime where the isolated nodes would disappear. And that's not hard to find. And because the Campbell-Mackay formula tells me that this would be the expected number of isolated nodes, right? N is the intensity, and this is the probability that, let's say, the origin is isolated. There's nothing within a ball of radius 2r. Theta d or theta, sometimes I'll write just theta. I mean, theta is the volume of the unit ball. Right? So from here you can see that if I replace this R by Rn to so Rn satisfying this equation here, that would tell me that the expected number of isolated nodes will converge to some constant. So the expected number of isolated nodes would stabilize. Now you can see that for connectivity already you require an additional factor log n here. So the percolation threshold is something like 1 over n in the dense network. So when you go to the extended network, the percolation threshold is of the order of a constant. Here you need this additional factor log n. So one can actually show that in this case, the Wn actually converges to a Poisson converges in distribution to a Poisson random variable with this mean. Okay, one can show this using the, for example, the Stein's method. Now, so just as we had a sharp phase transition in the thermodynamic regime where percolation happens, what Penrose showed, of course, this reference is not the latest reference for such a result. This result was probably proved in the late, like 1999 or something. But you will find this and more general results in Penrose's book, Random Geometric Graph, which appeared in 2003. So what happens is that if you look at the radius regime here, so if you have a constant c here, then you see that the expected number of isolated nodes is non-zero, right? So obviously if you want to eliminate isolated nodes, this constant must go to infinity, right? So essentially that's what this result says, that look, if you look at Rn to be log n over all this, plus something, where if this goes to infinity, then the probability that graph is connected goes to 1. If it goes to, if it's minus of this, then the probability the graph connected goes to 0, right? So now the more remarkable result there is the following, which says that the probability that for any Rn, you take some Rn, the probability that, not necessarily the one that is there in the previous slide, so the probability that the graph is not connected but has no isolated node, right? So that probability is going to 0. What that means is that in the random geometric graph, when you start increasing your radius and you stop, the moment every vertex has at least one neighbor, right? And then you step back, you will see that the whole graph is actually connected with a high probability. Okay? So it's basically these isolated nodes that are the kind of impediment to the graph fully getting connected. And the moment you, each one, so so essentially if you take the radius to be the largest nearest neighbor distance in the graph, your graph would be connected. That's right. So this is, but the proof here is much, much harder than in the Erdős-Renyi graph. When they're going from the percolation threshold to the connectivity threshold is like half a page of proof or something like that. Here, this is a very hard result to prove, and there is still a lot of other cases like the random connection model, for instance, where this is still open, or the inhomogeneous random graph, where this thing is still open. Yes? No, this is more, has to do more with geometry. So what it says is that when Wn is 0, it means that every component is of size at least 2. Now when every component is of size at least 2, you have to show that it occupies a certain space. And when it occupies a certain space, the total region that you require to be, that there should be a gap, right, where there is no point, that is way too much. So that's, and then you have to show that such a thing doesn't happen anywhere in the graph. So what you got to show is that there can't be, so once a component has a certain diameter, you have to show that that component cannot be isolated because it will have such a large boundary that the strip around the boundary, for there to be no point there, that probability goes to 0. And then you also have to show that there cannot be components of a very small size, given that all components are of size at least 2. So you have to get some lower bound on the diameter of the components and then show it. So it's very much to do with the underlying geometry of the thing. So you can't use a branching process. Branching process arguments here don't work because you see you have space, right? So you have a lot of dependencies and things like that. So the proofs here are much harder as compared to the Erdos-Renyi graph. Say Erdos-Renyi graph, when you try to prove the percolation threshold, you can get it precisely what the threshold is, right? You can't get that here because there it is almost like a branching process. Initially it's like a branching process, and if you have a supercritical process which survives for some time, then they have to connect and things like that, right? So that doesn't, but the results are remarkably, you can see there is because the connectivity is again log n over n and things like that. So it's kind of deceptive. Okay, so let's come to the random connection model. Now in the connectivity regime, so now here we have to, for the percolation, what we did was we had this Poisson point process, and we had a connection function which was fixed. Now what we did was we were slowly increasing the intensity lambda, and we said that beyond a certain intensity you will suddenly see an infinite component or a giant component if you are in a large finite system. Whereas for the connectivity you will have to, like we did here with a random geometry graph, you have to kind of scale things, right? You have this radius is going now to 0 because you are now putting a larger and larger number of points in a small box, and so the radius that would be required to connect these points would shrink, right? So the equivalent of that is to find a sequence of parameter values such that when you scale your connection function, so this was your original connection function, you scale it by this Rn, right? So if, and this Rn typically would be now going to 0, right? So what is the result that was proved? That you now obviously in order to prove these results you will have to assume something about the connection function, the decay of the connection function, and if the connection function behaves something like this, so this is required just to make it integrable, and then for the scale connection function the number of isolated nodes will converge in distribution to a Poisson random variable with mean e to the minus I. So the result kind of looks similar to what you had for the random geometry graph, except the theta d, which is the volume of the unit ball, gets replaced by this. Okay. Now this result was essentially proved by just computing the moments of this quantity. Whereas in Penrose, he assumes a slightly more stringent condition on the connection function g, and it's a rather complicated condition on that, but essentially it's like you have an exponential decay, and then using the Stein's method you can get bounds on the rate of convergence of this Wn. Not only you prove Poisson convergence, but you also get bounds on the rate of convergence. Okay? Now one can, like in the random geometric situation, one can try to prove certain strong law results for certain quantities in this graph, like when do isolated nodes disappear and things like that. In order to do that, what one needs to do is to, now if you want to prove strong law, you will need to couple your point process. So what one does is one can couple these point process such that the number of points when you go from n to n plus 1 and so on is non-decreasing. Okay? So every time you add a unit intensity Poisson point process in the cube. And for each I and j, a priori you have this kind of IID sequence of uniform random variables. And then what you do is you draw an edge between xi and xj if this uij is less than g of the distance divided by r, right? So what you can see is that if xi and xj are in Pn, they are obviously going to be in Pn plus 1, but the edge may disappear, right? Because your r will also change with your n, right? So, but nevertheless, it's very nice way of, very simple and nice way of coupling all these graphs to see how when the number of points changes, what happens to the underlying statistic that one is trying to study, right? Is there some nice stability in that and so on? So now you need to, so WNR as before is the number of isolated nodes in this graph. So what we can do is we can define the analog of the largest nearest neighbor distance So again, we are kind of trying to get to connectivity, which we don't have. So first step would be to look at isolated nodes, right? What happens to isolated nodes? So if we take R, if we take the smallest value of R for which the isolated nodes, the number of isolated nodes is 0. So if you just go below this Mn, then isolated nodes would start to appear, right? So this is the kind of analog of the largest. So if you take G to be your indicator function, like in the random geometry graph, this would be exactly the half of the isolated nearest neighbor distance. So if the connection function decays in this fashion for some C greater than D, then what one can show is that the lim sup of this largest nearest neighbor distance behaves like log n over alpha n. And for the lower bound, one needs a slightly stronger condition, and it's not clear how to get rid of this. One can show that the lim inf is greater than this quantity here. And of course, if the connection function is decaying exponentially fast, then this holds for all C. And so what you get is that these two are the same. So the largest nearest neighbor distance essentially behaves like log n over n alpha. Okay. So if you're a little bit above this, then you would almost surely, as n goes to infinity, not see you would not see isolated nodes for large. Okay. Now, so I'll probably spend less time on this here. So what one can do is, I'll explain this for the inhomogeneous graph a little bit later, but the idea is something as follows. So one would like ideally to show that when in your graph, when your scaling parameter is larger than log n over alpha n, your graph should be connected, right? That's what this result says is that if your scaling parameter is larger than log n over alpha n, then you don't have isolated nodes. Ideally, one would like to get a result similar to the random geometric graph, that at this threshold, the graph also becomes connected. That's what one would ideally like to show. One doesn't have that result quite, except in that paper that I was mentioning by Penrose, where the connection function has compact support. So when connection function has a compact support, then one can show such a result, right? So that's been extended. But in general, for graphs of this nature, this problem is still open. Now, what you can actually do is to try and leverage the result that is already known. So how do you connect the graph? What one does is the following. We know for the random geometry graph that if this radius within which you will join all the, you will draw an edge between this and the points which are within this ball, if this if b is greater than 1, so this is my Rn tilde, let's say b. So if b is greater than 1, then I know that if I look at the random geometry graph with this radius, then the graph is connected, right? Now I go to the random connection model, and what I say is that, look, I know that, of course, there will be a certain fraction of nodes here to which I won't have direct edges. But what if I try to find a regime? So what the idea is the following. So this is gamma log n over n alpha. Alpha is the integral of the connection function. So what I want to do is to try to find a gamma which is large, so that to every one of the nodes in this box, I have a one-hop path. Okay, right? So suppose I find a gamma so that either I have a direct path or a one-hop path. So now you can see that if for every vertex I can show that with high probability there will be a path to every one of these nodes, either a direct connection or a one-hop path, then that would tell me that the whole graph would be connected, right? And so that's the kind of idea that gets us to some condition of this nature. I think one can improve this condition. This doesn't seem to be the optimal one. So there was this inhomogeneous random graph that was introduced by Penrose. This appeared recently. This was in arXiv very recently. So here the inhomogeneity is slightly different. So you have a vertex set which is an inhomogeneous Poisson point process with intensity n mu, where mu is a probability measure. And your connection function G, which is symmetric, it satisfies a certain rather strong condition. What it says is that the minimum, so you have inhomogeneity in both the underlying distribution of the points as well as the connection function, okay? Fine, so where your connection function. But then what you need is that for all n, your minimum expected degree, right? You go to any point and your number of points it connects to is a inhomogeneous Poisson process with a certain intensity. The minimum, where the expected degree is minimum and maximum, that should not be the ratio should be bounded away from 0. And this doesn't seem to be such a terrible condition, whereas this seems to be rather stringent. You require the connection function to be bounded away from 1. Now you can see that this graph is very, very general. You're allowing for all kinds of underlying distribution of your points as well as all kinds of connection functions, but you want the connection function to be bounded away from 1. Okay? That seems like a rather stringent condition. And if you look at the number of vertices of degree j, then what he proved is that if the expected number of, if you can find a radius, if you can find a scaling parameter for these connection functions such that the expected degree stabilizes, then you have a Poisson limit. So it's a very general result, but then it requires this rather strong condition. For example, it doesn't include the simple random geometric graph, right, where the connection function is 1 within the unit ball, right? But again, this problem in trying to prove any sort of Poisson convergence with these kind of random connection model, this condition seems to be a rather strong bottleneck, this connection function being bounded away. So in the random geometric graph case, because the connection function is 1 on a certain ball, right, we have a very specific form for the connection function. It's a very simple form. One can actually use it to push the calculation through. But for a general connection function, this is the major problem in the computation. So if we come back to the inhomogeneous random connection model that I had mentioned earlier, and this part is a joint work with my student Sanjay Jahwar. So this was the connection function, again, the g of x comma y, and this should be mod x minus y to the alpha. So if one takes the radius, the scaling parameter. So what we are going to do is we are going to look at Gn, which would be g of this x mod x minus y over Rn, okay? So if your scaling parameter is given by this function here, where C0 is this constant, of course you will see conditions on these parameters when I state the theorem. So if one takes, so you see this log n term come here. So this is the radius, this is the scaling parameter. So if we consider the inhomogeneous random connection model that we had in the previous slide, so you have a homogeneous Poisson point process on a torus of intensity n, and your connection function is given by this function here, scaled by this Rn of xi, right? So if alpha is greater than d and beta is greater than 1, then two things. So if you recall, the Penrose's result said for a general case that if the expectation stabilizes, then you have a Poisson convergence, but you require that the connection function is bounded away from 1. But in this case, you can see that for any x and y, if the weights can be arbitrarily large, your connection function can get very close to 1, right? And that's exactly what the problem is with, even though here you have a specific form for the connection function, it's somewhat complicated because of the weights bringing in dependencies. One needs to be kind of careful, and then what we are able to show is that if your alpha beta is greater than, so this condition seems to be okay. I mean, there's this annoying condition which we are not able to get rid of. So if alpha beta is greater than both of this, typically this is not such a bad, because if you want heavy tail distribution, your alpha you would want to be small, not too large. Alpha should be kind of close to D. So in that sense it is okay, but ideally one would just like, if one looks at the other results, like something like this, just alpha beta greater than something. Then what we are able to show is that the number of isolated nodes, so we don't still have the result for vertices of degree j, which would probably bring in some j plus 1 log n or something like that here. We have only for j equals 0, that is the number of isolated nodes converges to a Poisson. And again, what we would like is that under this scaling regime, if I just get rid of all these things and I put a constant here which is larger than 1, then the graph should be connected, right? But unfortunately that, at least at this time, I mean, it seems quite daunting to prove that the graph would actually be connected with high probability under this kind of a scaling regime. But we have been able to get, again, kind of sufficient condition for the graph to be connected. So there's a whole lot of stuff that one needs to compute here. You finally end up with a constant rho, and the idea is the same. So it's kind of leveraging what you have for the random geometric graph. So what you're essentially saying is that, look, if I have an edge to everything within some b log n over n theta d, then if I look at this new graph with these edges, then my graph is connected, right? And so what one tries to do is, I mean, there are many ways to, I mean, it's not probably quite optimized in that sense, so one can probably look at it more carefully and see which regions one is expected to get this kind of one-hop path. Maybe these are one-hop paths just which are nearby, right? So you can, one can, there seems to be some scope here for maybe optimizing this a bit more, but already it kind of gets somewhat complicated. So what one can show is that if you finally end up with this parameter rho here, and if your scaling parameter is given by this function here, and if this gamma is greater than this rho, then your graph would be connected with a high probability. Now, of course, in this case, we just need the condition beta greater than 1 and alpha greater than d. Okay? So these are the minimal conditions. Beta greater than 1 ensures that the weights have finite mean. That's definitely required. And alpha greater than d requires that your degrees are finite. Okay? So just under that mild condition, we can show very simple. The proof is much kind of simpler. Perhaps if one can optimize it, one can probably push it to make this row somewhat smaller. So ideally, one would like this row to push it so that it is 1, right? Then we have the result that, okay, when isolated nodes disappear, your graph is kind of connected, kind of thing, right? Okay, that's right.
Okay, if the decay, so even when you had r to the power minus c decay, which is, in some sense not as quick as the exponential part, you still weren't able to get. Okay.
Yeah, that doesn't really help much. It's these kind of long edges. No, of course, this graph has much other very nice properties. It has this kind of small world behavior. It also has, I think, the ultra small world behavior. You pick two vertices randomly, the distance is log n. So you get many of those very nice properties. Like you have even probably just even short cycles, or all those kind of things. So it's not locally tree-like and things. So of course, that is true for any random geometric graph case. You won't see anything which is locally tree-like, and that's why you won't have those branching process kind of arguments won't work. You have to use the geometry to